Assalamualaikum and hi, my name is Muhammad Inish. My now metric is BE2500109. And today, our group will be presenting and focusing on designing an off-grid solar photovoltaic system for a double-story residential house. Electricity is essential for our daily life. We use it for lighting, cooling, cooking, communication, and many other household activities. Currently, most homes in Peninsular Malaysia receive electricity from the national grid, which still depends largely on fossil fuels. To reduce this dependence, we propose on off-grid solar PV system, which generates electricity directly from sunlight and operates independently without relying on the DNB grid. The problem statement. The problem is that the homeowner, Haji Jamil, requires a reliable electricity supply without depending on the TNB grid. In addition, the original design contains several inconsistencies, such as incorrect calculation for daily energy consumption, battery sizing, PV losses, and economic assumptions. Therefore, our project recalculates the entire system using consistent assumption and correct engineering formulas.
Hi, my name is Mohammed Faibi Mahat, metric card 250113. So I'm going to explain our objective in this project. So for the first objective, we want to calculate the connected load, maximum demand, and design current of the selected house. And our next objective is to design a suitable conceptual of grid solar PV system. Our third objective to determine the required PV array, battery bank, inverter, charge controller, and protection rating. Our next objective is to estimate the initial cost and simplify the payback period of the proposed system. Next, to compare the environmental impact of grid electricity and solar PV operation. And lastly, our objective to identify the limitation and safety requirement that must be checked before installation. That's all our objective.
Parameter and assumption. Before performing the calculation, we establish several design assumptions. The house is a double-story terrace house with a 240-volt single-phase supply. We assume a power factor of 0.85, a demand factor of 70%, 5 peak sun hours per day, and an overall PV derating factor of 0.75. For the battery system, we assume 80% depth of discharge, 90% inverter efficiency, and 1 day of battery autonomy.
Okay, for the next slide, I will continue to our design of the house. So this design, we draw the design in the AutoCAD, and for the ground floor design, we have a 10 lamp, 4 ceiling fan, 12 socket, and one aircon for the bedroom, and one television in the living room, and one water heater in the bathroom one. Also, the in this ground floor have the two laptops in the ground floor. This is all the load that have in the ground floor. So I will continue for the next floor, which is the first floor. For the this floor, they have also 10 lamps in every room and every area, and they have four ceiling fans in every room and in one in the family area. And they have 11 socket. They have three aircon in every bedroom and one television in family area and two water heater in bathroom 2 and bathroom 3, and also one half laptop in this first floor. So that's all for the loads in this floor, first floor. So next, I will continue with our load assessment. This is the slide that I will explain about our total load in every appliance and load that we use. For the first appliance, which is the LED lamps, the total quantity is 20 20 nos, and the power unit that they its use was 12 watt, and the total connected load was 240 load. Same goes to the ceiling fan. The total have a 8 unit power is 75, and the total load watt is 900 watt power. And for the LED television, they just have a two, but the unit power is 150. So the total load power is 300. For the refrigerator is one only, and the unit power is 300. So the total load is 300. For the washing machine, also one, and the unit power is 500. So the total load for the washing machine is 500. So next we go for the other appliance. For the aircon, we have four quantities, and one each unit power was 750 watts, and the total of all aircon power is 3000. Next, we go for the rice cooker. The quantity is one, and the unit power is 700, and the total was 700 watt lah. Next, we go to the microwave oven, which is have one only, and the unit power is 1200 watts, and the total is 1200 watts. For the laptops, we have three laptops, and each laptop the unit power was 95 watt, and the total was the 195 watts. For the iron, only one iron they have in our load, and the unit power was 1000, and the total was 1000. So for two more appliance, which is water heaters, we have a three units, and each unit power was 3600 watts, and the total load power in the water heaters was 10800 watts. And lastly is a water pump. We have one quantity, and the unit power was 400 watts. So the total power load is 100. So to calculate the all load power, we just uh, sum it all in one line. So first to 214 plus 900 plus 300 plus 500, 50,000 plus 700 plus 1,200 plus 195 plus 1,000 plus 10,800 plus 400. And we're gonna get 19 1,235 watt, and with this on watt we multiply with the demand factor, which is 0.970, and we'll get 30,000.47 kilowatt.
Assalamualaikum. My name is Muhammad Yusuf Mirujan. My matric number is DE250024. For the design current, we use the standard formula and the calculate value is 66 ampere. Next, for the MCB selection, we follow the condition IB is less than IN and IN is less than IZ. Therefore, we selected an 80 ampere MCB because it is higher than the design current and still within the cable capacity. Lastly, we selected a 100 ampere 30 milliampere RCCB to provide protection against a leakage and electric shock. This slide shows the daily energy consumption of the selected appliance. The water heater has a power rating of 10.8 kilowatt and operate for a 0.42 hours per day, resulting in 4.5 kilowatt hours of energy consumption. The water pump has a power rating of 0.4 kilowatt and operate for 1 hour per day, consuming 0.4 kilowatt hours. After adding the energy consumption of all appliances, The total daily energy consumption is 27.9 kilowatt hours per day. For sizing purpose, this value is rounded up to 30 kilowatt hours per day to allow for small operating uncertainties and system losses.
So our source of renewable energy that have been chosen is sun, which is we use solar PV. So to know how much solar PV that we need to be used, we must first calculate the required PV capacity. So to calculate the required PV capacity, we need to divide the daily energy divide by peak sun hours multiplied by the rating factor, which is daily energy is 30 kilowatt per hour. We divide it by the peak sun hour, which is 5 hour, and the derating factor 0.75. So PV capacity that we gain by calculating it is 8 kilowatt. So we need to calculate the number of modules. So we get the PV capacity before, which is 8 kilowatt. We divide it by 500 watt. So we get the number of module each 14.55. However, the minimum calculated quantity is 15 module because but we need to consume it, which is 16 modules, which are recommended to provide a more practical generation margin and a balanced array configuration subject to the selected inverter and MPPT voltage limit. We continue with our selected PV array. We select 16. So by the number of selected PV array, we multiply it by 550 watt, which we can get 8,800 watt. So we need to calculate the daily net PV energy, which the normal solar energy that been used daily. By the value of before selected PV array, we get 8.8 k watt. We multiply by 5 hour per day. We multiply by the rating factor, which is 0.75. So we can get daily net PV energy 33.0 kilowatt hour per day. So we calculate our annual net PV energy. So the value of 33 kilowatt hour per day, we multiply by 365, which we can consume it by a year. So the annual net PV energy we can get is 12,045 kilowatt hour per day. So the estimated annual production exceed the design energy requirement of 10,950 kilowatt hour per year by approximately 1,095 kilowatt hour per year. In an off-grid system, this excess is not automatically sold to the grid. It provides a margin for variable weather and may be curtailed when the battery is full.
Now, let's look at the battery bank design slide. Based on our daily target of 30 kilowatt hours, we calculate the required battery capacity using the formula on the left. By including an 18% date on discharge and 90% inverter efficiency, the calculation gives us 868 ampere hours. For a practical design, we selected a 48 volt 1000 ampere hours lithium battery bank. This gives us a total stored energy of 48 kilowatt hours. After factoring in the efficiency, our usable AC energy is 34.56 kilowatt hours, which is successfully meet our daily target. However, as highlighted in the note, a 48 volt system running a large 20 kilowatt inverter will produce a very high DC current. To handle this safely in a real situation, we must use manufacturer approved module, heavy duty bus bar, proper fuse, and thick cable to avoid overheating. Now, let's look at the inverter and charge controller design slide. First, for the inverter rating, we multiply our maximum demand of 13.47 kilowatt by safety factor of 1.25, which gives us 16.88 kilowatt. Based on this, we select a 20 kilowatt pure sine wave of rate inverter. During actual installation, we will ensure it is compatible with motor starting current, compressor surge, and our battery management system. Next, for the charge controller, we calculate the normal charging current by dividing 8800 watts by our 48 volt system, which gives 183.3 amperes. Apply a 1.25 safety factor, bring our design charging current to 229.2 amperes, or roughly to 230 amperes. To support this, we require a total MPPT capacity of 230 amperes. We can achieve this by using two 120 amperes controller or an integrated inverter charger. We will finalize the exact solar panel connection once the specific module voltage are known.
For system cost estimate is component is 16,550 watt. Solar module is 15,400 ringgit. For lithium battery 22,500 ringgit. For 20 kilowatt of grid inverter is 7,000. For MPP controller total 230 M is 5,000 ringgit. For mounting structure is is 2,000 300. For component wiring, insulator, fuse, SPD and protection, the cost estimate is 2,500 ringgit. For installation and testing, the cost is 4,050 4,500 ringgit, and the estimate total is 58,200 ringgit. For economic analysis, for annual energy demand, the calculation is 30 kilowatt per day times 365 equal 10,950 kilowatt per year. For net annual saving, assume routine maintenance of 400 per year. Net annual saving, the calculation is 6,241.50 minus 400 equal is 5,841.50 per year. The avoid For avoid annual grid cost, the calculation is 10,550 minus 0.57 cents equal 6,251.50 cents per year. For equivalent monthly value is the calculation is 6,241.50 over 12. The, the total is 520.13 per month. For simple payback, the calculation is 58,200 over 5,841.50 cent equal 9.96 years and equal 10 years to simple payback. 20-year illustrative life cycle view. For item 20 years avoid rate cost equal 124,830. For initial system cost, the value is 58,200. For routine maintenance, for 4 year 400 per year minus 20 is 8,000. For item 1 assume battery replacement, the value is 22,500. An illustrative net benefit after 20 years is the value is 36,100. The environmental impact for avoid emission 10,950 kilowatt per year times 0.740 kilogram CO2 per kilowatt equal 8,103 kilo CO2 per year minus 8.10 tons CO2 per year. The energy consumption report a provisional 224 grid emission factor of 0.740 kg CO2 equivalent per kilowatt for Peninsular Malaysia. Over 20 years, the gross operational avoidance would be appro- approximately 162 tons CO2 equivalent. For the conclusion is the corrected electrical design feature a connected load of 90.24 kilowatt, a maximum demand of 30.47 kilowatt, and a design current of approximately 66 amp, which will be initial protected by an 80 amp MCB and a 100 amp 30 milliamp RCCP to support a daily design consumption of 30 kilowatt per hour. The proposed solar system consists for 16 550 watt module generating 8.8 kilowatt and pair with a 20 kilowatt power sine wave inverter, a 48 volt and 1000 Ah battery bank, and a 230 MPPT controller capacity at an estimated initial cost of RM 58,200. The system offer a 10-year simple payback period while mitigating 8.10 tons of CO2 emission annual relative to the Peninsular Malaysia grid. However, because annual energy balance cannot guarantee an uninterrupted 24/7 power supply, site measurement, detailed production design, a robust backup strategy, and competent person certification and strictly required before physical implementation. Thank you. That's all for me.